Okay, let's get started. To save some time, I actually copy entire directory tutorial to my local machine, which actually the latency between them is not too good. Um, so I just copy this particular tutorial 04 SSP, and this directory contain this like 5 different files. So we're gonna explain today. Uh, and let's quickly talk about this make file that you're gonna run. So uh, if you're not familiar with this make file, it really doesn't matter. But basically, if you type O or if you just type make, then this program will be created. Something written in this O directory, the variable in the make. So basically, we're gonna create 4 different files. As I just click here. So if you type make, we're gonna create this 4 file. And they're going to create the different binary from the Crack Me challenges, the Crack Me source code. So Crack Me source code here is the exactly same source code that we've been singing so far, which is allocated buffer and print out these messages and scanf, compare the secret value and print OK or invalid path, right? That's interesting. But we're gonna generate 4 different files from the same source code by applying all different sorts of or changing their compilation parameter. For example, in no SSP exec, so we're gonna provide this flag and no stack protector, but we're gonna enable stack executable. We're gonna make the stack executable in the program. Similarly, for no SSP but no executable, basically we didn't put any canary value, but we're gonna make the stack non-executable so that you cannot just inject the shellcode into the program. And when it comes to SSP exec, we're gonna enable the stack protector, and we're gonna enable the executable stack, meaning that you can place the stack payload to your shellcode into the stack, but you can actually jump there. And this is the most modern, our say default implementation of mitigation. Basically, no SSP enable and no exec. Meaning that your stack is not executable, the stack protector is enabled. In fact, this is default behavior of the most compiler. So we're gonna create for this binary by typing make. So these are the actual parameter that ended up using, but only differences again, this stack parameter and exec stack. The rest of them are not too important. So whenever we done compiling, so we're gonna actually dump this checksec output. The checksec is one utility that provide a basic security mechanisms, starting from the relocation read only. We're gonna talk about this all in the later lab, so you don't have to worry about. What's important today is about this stack canary. So given a binary, the first thing you have to do is you run checksec and see if their basic condition of mitigation, whether canaries exist or stack is executable, which is located here. You say non-executable disable, meaning that stack is executable, or you can write or execute at the same time. And PIE is enabled or not, is a position dependent executable, kind of randomizing location of your text sections and or entire binary image onto the memory. So we're going to talk about this later lab, one by one. So about focus of today here. And somewhat we like to highlight the behavior through NX as well. So if you disable this stack canary and executable stack, enable the executable stack, then you say no stack is found and stack is executable, meaning that the NX is disabled. On the other hand, if you provide stack, no stack protector and enable mitigation of NX, it say stack is not executable, but got no canary value exists. And this is the most secure one. So stack protector is enabled and exec stack is disabled. meaning that you cannot put the payload to the stack and canary exists. This is again default value of the modern compiler, and this is the most of the binary these days contain this value, contain this mitigation in their binary as well. Okay, I like to highlight their differences result by having this tool called diff. This diff is nothing but to diff the certain section of the binaries. Basically, this when you type this, we're gonna provide two parameters for the comparison and provide the diff between them. It seems like a little bit complicated result, but you can consider the disassemble result of the main, right? So we're gonna launch the diff, and we're gonna provide one executable at a time. So what about the diff between something that we enable the stack protector but no executable and executable? Surprisingly, there is no difference between them in terms of actual code, because non-executable is kind of independent to the binary, but it's written in the form of flag in the ELF. So in terms of actual code output, doesn't change anything. And whenever the operating system see those are flagged as part of the ELF, they actually enable or disable or set the permission of the stack location or permission of the stack, whether it's executable or writable in the system at the runtime. But what's interesting here, so what if we provide two different binary with executable, but stack protector is enable and stack protector is disabled? Well, we better just reverse this guy. So we're going to provide the same condition, but here we're going to do, so we're going to compare these two conditions. No stack protector is enabled, but we're going to provide another one that enables stack protector. So there are some differences between them, as you can see here. Let's visit one by one. So there are a few differences in terms of actual instruction, because if you enable stack smashing protector as part of GCC, they actually put the canary value as a result. And we're going to see what is canary value in here. Apparently, the difference is here. This is what original value, original binary contain. We reserve the stack in the original form. And this is another interesting call. It's basically get the instruction pointer of the next instruction, which means as a result of this, EBX register will contain the instruction pointer here. And similar to what we did when you're writing shellcode, and this is a simple thumb program that contains the instruction pointer in 32-bit architecture. And instruction pointer now pointing here in EBX, compute something, right, and start executing. On the other hand, in terms of actual stack frame, with the stack smashing protector, they actually reserve a little bit more, about 8 bytes more than the previous one. That's interesting. And they actually do the same for getting instruction pointer. Likely these two values that they're deferring is exactly the same. But what's interesting here is these two, what's happening in here. So they get some of the value from GS register or segment, or more precisely, this is a segment register that is defined, the location is inside the kernel. So basically, depending on the value in here, the only runtime know the exact location. In fact, this is a simple convention that Linux loader and GNU libc or GNU loader put some of the random value or canary value for the program. So when programs launch through the dynamic linker or loader, and they actually prepare TLS sections, what we call typically pointed by GS register, and GS register contain in this particular offset, they contain the canary value. And this canary value will copy to EAX, and EAX will be put to the stack in this instruction. It's basically EBP minus C, meaning that on top of the EBP register, right? Location of the frame pointer, in order to protect frame pointer as well as the return address. And once you put the canary value to the stack right before frame pointer and return address, in fact, they're going to clean up the value inside the EAX, right? And the rest of the instructions are exactly the same. So at the prologue of the function, they do extra to prepare some of the, copy some of the canary value and put it right before the frame pointer. So in order to protect them. What's interesting at the end in the prologue is a way to compare those. So this is what's happening here. So previously there is no such comparison routine, but in the newly compiled one with SSP, and again, they're gonna, do you remember the location that we put the canary value? And copy this one to EDX and compare this location with the GS register, which is the original value of the canary. And it seems like one of the comparison routine instruction was omitted, but after, if they're different, they're gonna call the stack check fail so that the program will be stopped as a result. So do you guys see the differences between these two binaries? And let's try something. Then what if we provide like a little bit bigger one for no stack protector, like this guy? The program just crash, right? If you see the core, instruction pointer is hijacked. That's what we've been seeing so far. So if you provide the SSP like this, it says stack smashing detected, and program actually willingly terminated. Although for convenience reasons, they actually provide the core. Let's check. But interestingly, they actually stop in the normal sense. They actually not crashing. They actually abort. But they stop the program by invoking abort system call. So meaning that actual program just stop because they sense the potential attack going on. And interestingly, they say stack smashing detected, so everything is terminated as a result, right? With the nice messages. So in other words, in this particular environment, we cannot actually attack this program thanks to the SSP mitigation. Although this program has a vulnerability, the exact same vulnerability that we exploited last week, thanks to this SSP mitigation, we cannot exploit anymore. So pretty interesting, right? They kind of, by introducing mitigation, so that make it impossible to exploit this particular setting. But you guys also will learn about, even under such a mitigation, there's still way or a lot of interesting way to bypass by leveraging the computation environment or execution environment at the time as well, right? And but this is not the today's task, but today's task is relatively easy. But we're gonna talk about this crack me, but this crack me is compiled with a what we call constant stack protector, what we call that beef canary. Is basically they're using canary value as a that beef as canary value. So in order to bypass them, so you cannot just touch the canary value, and you should still override the return address or frame pointer depending on what you like to do, right? So let's quickly discuss about what's inside this target SSP. This is the program that we're going to exploit today. So I actually open up Jydra here. This is target SSP. If you go to the main, you can see that this is the compilation output. This is a main function, has a buffer, and after send your ID call, is print out the banner and scanf, string compare, and depending on the result, to say password okay or invalid password, right? In fact, if you actually see the crack me challenge, original source code it looks exactly same, right? Literally exactly same. So in this case, only difference is there's some, I'll say local variable assigned in order to make the usage of the local variable clear, which is nice. So that you can say this is 3 different call instead of just 1 line here. Similarly, for the string compare, they break out the call from the string compare and compare here as a result. So other than it seems like benign. But what's interesting is this canary one. So do you guys recognize here? It's the exact same pattern of the program, but there's one interesting thing happening here. So basically, here. So basically, what's happening here at the prologue of the function, before they execute any logic of the program, they insert on top of the EBP, they're gonna actually insert that beef value somewhere, right? In order to protect the program. So at the end, here, right before returning back from the program, they actually compare the canary location with the that beef. That's interesting. And then if it's 0, meaning that nothing happened, exactly the same, then they're gonna return as if nothing happened. Otherwise, they're gonna load this, I'll say, stack smashing character, and they're gonna push to those value and start invoke error messages to the program. This is basically stop the program by showing these messages, kind of mimicking the SSP implementations in a little bit add-on manner, right? So these are the locations that we're gonna exploit. And these are the canary value we have to bypass. So when you're writing certain value to the program, then you can kind of understand we have to bypass, or in this case, the injecting this canary value is kind of easy. As far as we provide that beef, we can kind of bypass the canary checking in this case. And this is one of the fundamental limitations of the canary. As far as you know about the canary, as a part of the buffer, you can actually prepare them, because canary value, although attacker write the canary value or manipulate the canary value, the mitigation actually cannot detect the modified canary. As far as they concerned, they only compare the actual result, actual data inside this location in a little bit indirect manner, right? So let's exploit this guy. Now, how can you estimate the location of the canary? Again, you can kind of measure from the location of the buffer all the way down to the canary. In this case, canary located at EPP or -10 from the stack, and buffer located 10. Likely after overriding 16, you can kind of control the canary, right? This is one way to read the assembly, but also you can dynamically measure as well, right? Let me show how we can, what I mean. So first thing first, what if we provide the normal value, right? SD work as expected, right? Invalid password or valid password. What about we provide a little bit longer one, right? Then it seems the program says stack smash detected. So instead of crashing the program or hijacking the instruction pointer in this program, the program detect what's going on and stop. So our job is to figure out the location of the stack, location of the canary value here. So what is the right interesting way? Say, what about we try 20? Stack smash detected, which means we touch the canary value by providing 20. Right? What about we provide 10? It seems nothing happened. So what about we pick the middle, like 15? Nothing happened, meaning that after providing 15 character, which is still considered as a normal value, they didn't sense any override. Either the 15 is enough for the buffer, or we simply didn't reach the canary value. So increase a little bit, 17. It seems they detect the overriding. Right? What about we provide 16? We also say stack smashing detected. Does we include the end? Seems like it. So after 15, or 15? 15 is fine, right? After we provide 15, they start detect the changes of the canary, right? So in this case, what about we provide what's the least significant byte of the that beef? EF. So what we're gonna provide? So after 15, we're gonna provide EF. See if the program crash or not. I think because of the null character at the end. So basically, because of the scanf behavior, we start singing the null at the end. So basically, the idea here is that we're going to provide entire that beef, so that we can see if bypass or not. So we're going to provide this E. So we're going to provide this to the program, basically that beef. See, once we provide this that beef, it seems although we provide more than necessary byte to the program, and stack smashing happening right now, but the program didn't recognize it. Pretty easy. And then what about we provide cyclic value, maybe 20 or something? Then program crash. Then once you run the GDB core, let's say this particular location is overwritten, hijacked by us. So, so after 12, you start overriding them. So let's prepare some of the exploit against them. So we're gonna launch the payload. We're gonna prepare the payload. What was it? 16. That if. And that if. Right? It's basically once we bypass the canary value, there are some locations or dirty value in the stack. And then we're gonna control the return address here. So let's send the payload. Okay, program crash. Let's check the whether we control the instruction pointer. Seems we correctly hijacked the instruction pointer. What will be the next step? This particular one, if you run type checksec on this binary, you can say stack canary is not found in SSP sense, but we have a that beef canary. We can easily bypass in this way. And one thing interesting here is the stack is still executable. You can use the exact same technique that we studied last time, get the shell code from the shellcraft and inject it right after and jump there. So another way is that although this shellcraft has all the shell code for Linux operating system and platform like this prepare, In fact, you can actually easily write the shellcode by using shellcraft as well. This is one thing that I like to demonstrate to you as well. So what we're gonna do, let's say shellcode. You can, it's better to show here. There are a few interesting code they prepare here. For example, you can invoke open shellcode. Then in this particular case, they're asking file, some of the flag and mode, right? And if you invoke shellcode and open, they're going to prepare a assembly, corresponding assembly for you, right? For example, say we like to open flag and the read flag 0, then it actually return the corresponding assembly. So basically they have a template of those interesting code prepared for you. So as far as you provide all these value in here, following those pattern, then they can actually generate the list of the system code for you, which is pretty convenient as well. So what we're gonna do, so in order to read the pro flag, what we ultimately like to do with the pro flag, with the read parameter, and read the buffer, the file descriptor of the return value, right? Likely located in EAX register from this open system call, right? And read to a certain buffer and large enough size, say this amount, and buffer now contain, you can say you can put into the ESP, for instance, as a buffer, or you can put anywhere you want. Based on the condition in the execution environment, right? And say buffer, and write a value to the console. So basically, you can write to the standard output of the program, the entire buffer with the amount of data that you read. So we like to prepare this exact sequence of code. So let me show you how we can do. So we talk about this read pretty, we could create the list of assembly for read pretty easily like this. But at the same time, you can also do write as well, open read as well. And in this case, we're gonna use the EAX, which is the return value of the previous open system call. And then we're gonna do a buffer, say ESP or 84. So we're gonna put a value here. You can also do, say, deadbeef. Then they're gonna put the buffer into the deadbeef as well, right? They're gonna put deadbeef here, or if you want, you can put ESP, and they're gonna use the ESP as a second parameter. If you want to read, you can see this the simple patterns as well, like this, pretty easily. So what we're gonna do is that we're gonna just chain this one together in programming way, shellcraft, open pro flag, and then we're gonna read EX to, but where should we put the buffering? This is a previous crash that I just run, and there are many places you can actually put stack in. Is that the executable? Oh, it's a PIG enable. So one simple way is stack is not executable, so you can pick one of the value in the stack, or assume I wanted to use some of the global data, but it seems like the binary is randomized. So instead, we can either use some of the stack location that no one is using, For instance, you can use maybe here. You just put the arbitrary location in the stack because we are not going to touch the rest of the data anyway. It's big enough, right? So we're going to start from here. About 1,000 of characters, see if it's actually working. And size 80, 48. Right to the buffer. What is the tool? IPy is IPy is just IPython. IPython is just yeah. But I don't like when I type IPy, they just import the font tool. You can do just IPython 2 from and now I include a bunch of tools for the convenience, but it doesn't. Yeah, so that's what it is. And also here, once you prepare the assembly, you can clean out the shell. And as part of this, you can compile at the time and clean out. But when you compile this, you have to specify the context of the architecture. So see if it's working. First, check the actual assembly first. It seems they prepare a pretty good chunk of assembly for us. We should read and put it to the certain locations and write. The first, one caveat is that hopefully this one is injectable to the process, but it seems like there's no concerning bytes, I guess. But just in case, we're gonna say convert the shell to assembly form, and we can dump the outside, and then we're gonna append the shell at the end. So I launched the program, and program crash. Again, we didn't change the instruction pointer, but before we do, we like to check the shellcode is correctly injected to the binary, right? So this is instruction pointer is in the depth beef, and we like to check the location of the stack. And what would be the value after that beef? So I can see the interrupt here, 2, 3. It seems there is no problem of character in the shellcode that we prepare. So it's a time to just jump. Where should we jump? We jump to the top of the ESP in here. So let's change this and see if it's actually working. Right. So do you guys see the location of the buffer that we're gonna put? In here, there's nothing here. Of course, it's just normal stack that no one is using. But as part of this, they're gonna put, I'll say, the flag into those locations. So see, program is shellcode is executed all these 3 instructions, and you can see the stack. Since program crashed, let's examine where is a flag. Right, this is the location that we pick for the location of the flag. If that's true, see, and because of the execution of open read and write, this buffer location contain those values. Right. I think this is it for the tutorial. I think you can easily extend this one for remote as if the previous one. One simple trick is that create the node inside the shell and clean up the environment of the process. Then you can do exactly the same what's happening here. right? And you can extend this one for the remote exploitation. Okay, that's all for tutorial. Thank you, everyone. And if you have any questions, feel free to leave any comment, any questions in the chatting window, and I can answer those questions first. Okay, thank you.